Did it ask you about recording?
Yes.
Okay. So hello again, everybody, and welcome to the part 2 of the lectures on machine learning of the QLS course. I'm Jérôme and Nikhil, and I'm presenting with Nikhil, and we will be talking about dimensionality reduction and again about cross-validation. We'll start with a quick recap of what you saw in part 1. So we talked in the first session about supervised learning and the two main categories that are regression, where we try to predict a continuous output. So for example, the blood pressure or glucose concentration or age, and classification, where we predict a binary or a categorical variable, for example, diagnosis. And two very important models for doing these things, linear regression and logistic regression. Nikhil also talked about regularization, so adding a penalty on the coefficients of these linear models to reduce their variance and improve generalization to unseen data, and how to evaluate the performance of the models when they are fitted, and in particular, the importance of evaluating models on data that has not been seen, that has not been used to adjust their parameters, and how this can be done with cross-validation. So I know this is a lot to hear about in 1 hour, so don't hesitate to refer again to part 1 as necessary. And I'll also repeat a little bit the notation that we're using. So we are trying to predict an output or outcome Y, for example, blood pressure. And to make this prediction, we use some information about the subject, for example. So some predictive features that we can represent with a vector of values in our P. So we have P predictors or descriptors, for example, weight, height, some informations about this particular data point, and we use all of these informations to predict the value of Y. And we model Y as a function of these input features X plus some unmodeled nodes. So for example, and our goal when we learn is to approximate this function F. So for example, if we do linear regression, we take a linear function we look for F in the family of linear functions. So we model Y as some constant plus a linear function of X, the linear product of X and the vector of parameters beta that we need to learn. And learning in this case boils down to estimating the parameters beta 0 and beta that index the family of possible functions. So how do we do this? How do we choose the beta? We use training data. So we get samples, for example, of subjects if we're predicting if our data points are participants, for whom we collect the features, the predictors, and the outcome. And we try to find a value of beta that gives a good prediction on this training data, meaning that we have a loss function that measures the prediction error. In the case of regression, the sum of the squared errors. And we try to find a beta that minimizes this error on the training data. So finding beta 0 and the beta j, so that the sum of square differences between the true Y, the true outcomes, and those predicted by our linear combination of the mix of the predictive features is small. That is called fitting the parameters to our training data X and Y.
So just a note, in the previous slide, I think in part 1, the left-hand side of here is what we refer to as mean square error, so MSE formula. So that's exactly the same thing.
Exactly. Yes. Thank you. Here it's not divided by n, so it's just the sum of square errors. But yeah, in terms of the parameters, it doesn't change anything. So that was part one, and that's what we saw. We received some inputs or predictors X. We put them through our linear model here, and we obtain like this prediction Y. But as Nikhil explained when he talked about regularization, sometimes our model can be too flexible, too rich, and can approximate too well Y on the training data and then fail to generalize on the test data. And the more high dimensional is X, the more features we have in X, the more likely this is to happen. Because here I'm trying to find a mixture of the columns of X that approximate well Y. And if I have many columns, here I have many parameters beta to select, and I can find many different combinations of them that will fit very well Y on the training data. So I have too many decisions to make. I have a family of possible models that is too vast, and there is a risk of overfitting and also of finding unstable solutions. So in this second part, we'll add a step to this learning pipeline where we will first simplify the inputs X, reduce the number of descriptors of our participants so that our model is less rich, is more constrained, and we have a smaller number of parameters to select so that it becomes easier to find to identify the correct parameters, to find the associations between this reduced number of features and the outcome Y. So yeah, again, when we feed the model, we find an approximation Y hat of Y which needs to be close to the true outputs. And we build this approximation as a linear mixture of the columns of X. And if I have a huge number of columns in X and a huge number of parameters to set, as we said when we talked about regularization in the first part, I can build many different combinations of these columns that will yield the same result. So this makes it very hard to identify the correct parameters beta, and it can lead to big errors on the test data. It can lead to numerical stability issues because, as we said, for example, if the first two columns, sorry, it should be a 2 here, are very correlated, I can make beta 1 very big and beta 2 very small, and they will cancel out. So I can have several different combinations of beta that will yield almost the same prediction. And this means that if I get slightly different data, I might get a completely different solution. So that's why we want to constrain more the possible values for beta. So one way to deal with this would be to use regularization as we saw in the first part, or we can reduce the number of beta by reducing the number of columns in X. And finally, if I have a huge data matrix X and many parameters to fit, then the numerical procedure to do this will require a lot of time and a lot of memory to fit everything in the computer's memory. So that's another reason why we want to reduce the size of our data matrix. For the examples that follow, we'll use some toy simulated, very simple data just to illustrate the concept. So I'll just explain quickly how we created this data. First, we sample a data matrix with 3-dimensional features X, vector of parameters beta, so with 3 parameters, and some noise from Gaussian distributions. And we produce Y as a linear function of X plus some noise. And then, to see what happens when X becomes high dimensional, we add some columns to X that don't contain any information at all. So we start from a small matrix X like this, build Y as a function of this blue matrix, and then we add some columns to X that only contain garbage. And we'll see what happens if we add many columns, if we append many columns of garbage to our data matrix, to our design matrix X. And of course, as Nikhil explained in the first part, once we have our X and Y, we split them into training and testing set, fit the model on the training data, and evaluate its prediction, meaning measure the sum of squared errors on the testing data. So we do this while varying the number of features P. So we start from just the blue matrix, and then we add more and more features to X to see what happens. So here we start from just 3 columns in X, and then we add more and more features and see how the training and testing errors evolve. And we see that as I add more features to X, here the training error that is dashed goes down because I have many columns in X. I have many ways that I can combine them to fit very closely Y in the training data. So by combining these many columns in X, I can approximate very closely the output in my training data. But my model is overfitting, and it's basically fitting the noise in Y. So the testing error, when I try to see if it generalized to some new data that wasn't used during fitting, is increasing very rapidly, and my predictions are completely catastrophic. Just because it's hard to see here, just because the error becomes so big. Here is exactly the same plot, but with the squared errors displayed in log scale. And we see that the training error goes very low to 0. They start from 1, which is the actual amount of noise in Y. So mean error, squared error is the best possible is actually around 1. And as the model is overfitting, the training error goes down to almost 0. And here, if P continue to go up to reach n, the number of samples, the training error would go exactly to 0, while the testing error keeps increasing. So here, my model fits better the training data, but it's not improving at all. Its performance is on test data is becoming worse and worse.
So would you say, like how would we know how many features are informative in real data, or is that the question you're trying to usually tackle?
So in this data, we know because this is made up data, this is fake data that I generated, that I simulated. I know that in order to build the fake Y, I only used the first 3 columns of X. So in this case, the true number of informative features is 3, which is why adding more columns only degrades the prediction and doesn't improve it. On real data, that's something that's hard to figure out, and we'll talk about methods to try to see what is the correct dimensionality.
Cool.
Now, as I said, having many features also has a computational cost. So here I do the exact same experiment, augmenting the number of features P, and I just measure how long it takes to fit the model. And we see that naturally, as the number of features P augments, as the size of the data matrix augments, the time it takes to fit this model increases as well. And in this case, we're dealing with very tiny data because I only have 100 data points. So it remains very small, but it's increasing more than linearly, faster than a linear function of X. And actually with this, as we're fitting a linear regression here, with the solver that is being used, the time needed to fit the model goes with p to the power 3, and also with n times p to the power 2. So if my data were much larger than 100 points and p were becoming very large, asymptotically, the time it would take would look like p to the power 3, and it would start to take a very long time. So here with the 100 features, it's okay. But imagine if I were dealing with brain images, for example, that can have hundreds of thousands of voxels, fitting even an extremely simple model like a linear regression to this data would become very costly. So to deal with these problems, we want to reduce the number of columns in our input X. We want to reduce the number of parameters beta that we need to estimate. And the first very simple solution to reduce the number of columns in X is just to delete some of them. So I drop some of the columns in my design matrix X, and I fit the model on the remaining ones. That's a very simple idea, but if I choose correctly which columns to keep and which to remove, it can be very effective. So I give myself a budget, a number K of features that I want to keep, and then I will try to find the best ones to keep. And a simple way to do it is called univariate feature selection or feature screening and filtering. I look at the features one by one. So for example, if it's an image, I look at the voxel one by one and compare them to the output that I want to predict and try to see which seem to be associated with the output. So there are many criteria that I can use to decide if the feature is likely to be informative or not. Possibly the simplest ones, if I'm doing regression, so predicting something continuous like blood pressure, is to look at the correlation between the input feature and the target variable. And if I'm doing classification, is to do analysis of variance. So basically comparing the means of this feature in the different classes of Y. So to look at some examples, here I'm doing regression. I'm trying to predict Y, which is a continuous variable, and I have two features. If I look at X1, it seems to be quite well associated with Y, so it will probably be useful to keep it in my predictive model. I'm going to keep the first column of X, while if I look at X2, I see no association with Y, so X2 will be one of the columns that I will delete from my design matrix X, and so on for the other features. If I'm doing classification, for example, here in orange, I have patients who have a disease, and in blue, controls who don't have the disease, and I'm trying to separate them. Again, if I look at X1, the values of X1 for patients seem to be quite different from those that X1 takes for controls. So X1 is probably a useful information to predict in which class I am. Whereas if I look at X2, X2 behaves basically the same for patients here and for controls here. So it's probably not useful to predict in which class I am. And that will be a feature that I will remove from the model.
So yeah, since you mentioned the computational costs of the high dimensional, so do you want to comment on, is this trying out each feature also computationally intensive, or is it still better?
Of course, everything takes time, but here I'm looking at the features one by one. So I don't need to do any complicated computation to figure out how to best combine all of these features. So this kind of thing will take a time that is linear in the number of features times the number of samples. So usually it will reduce drastically the computational time. And also, for example, to look at correlation, I don't need a huge number of samples. So the fact that I have many features here ranging from 1 to p, for example, from 1 to 100,000. The other features, I don't care about them if I'm looking just for the correlation between x1 and y. So here, if I have a large data set, I can do this even with a subsample of my data set. So yeah, this will reduce computational time a lot. And now if I apply this strategy on this exact same toy data that we were looking at before, I still have in blue the testing and train error of the original full model. And now in orange, I do this dimensionality reduction strategy to keep only the best features. And this time I see that the test error remains small as well, even if I add many garbage features to X. Again, let's look at it in log scale. It's easier to see. So if you remember, if we use all of the features without feature selection, training error goes almost to 0, testing error explodes, the model is overfitting. Whereas if I screen the features to keep only the very few best, we have the testing error, which is only slightly higher than the training error. It will always be a bit higher, but it's close. And now we are more in a typical configuration of a model that is learning well. And both training and test error are close to 1, which is actually the amount of noise that I added to y. So that's the base error rate. That's the best we can get. Okay, so that was solution 1, doing feature screening. So simply deleting some of the columns of the design matrix X. And I put a link. You will see in the documentation of scikit-learn that they have many different strategies for doing this, but the basic idea is the same. But in some cases, maybe I can reduce the number of columns of X, but deleting some of them is not the best strategy. So for example, let's forget about Y for a minute and imagine I have my X data that is, well, here I'm looking at the first 2 dimensions. If it is like this, I see that there is a lot of variation again along the first column X1, and the second feature doesn't vary a lot in my data. So if I try to fit a plane to this data to predict Y from this with a linear model, even large coefficients on X2 won't affect Y very much because X2 doesn't vary a lot. So as the data is very narrow in the X2 direction, I might fit very different planes without affecting very much the outcome Y. So the coefficient that I estimate for X2 might be quite unstable. So I might want to here delete X2 from X in my feature selection and keep only X1 and try to model Y as a function of X1. But in reality, very often, the direction that I'm interested in will not be exactly aligned with one of the dimensions of my input data. So for example, if X1 and X2 look like this, here I'm basically in the same situation, and I might want to summarize my input data just by its position along this line instead of keeping 2 dimensions. But now this line is not aligned with X1 anymore, so I cannot just delete X2 or delete X1 to reduce the dimension of my data. So I have to come up with a different strategy. And there's a family of approaches to do this that we call linear decomposition methods. Okay, so just to reiterate on linear regression, we have for our sample a vector of outcomes Y. So for example, for each participant, we have their blood pressure, and we store that in a vector Y. And we also have, for each participant, many measurements that we store in X. for example, their height, their weight, and many other features. And we try to model y in linear regression as a linear mixture of all the columns of x. So we build an approximation y hat of y that is made by mixing together all the columns of x. And we try to find the weights beta that when we multiply the columns of x by the weight beta and then add them up, produce the y hat that is as close to y as possible. And as close as possible in the sense of having the smallest sum of squared differences between y and y hat. Now, if x has a huge number of columns, I have many parameters beta to set, and I can find many different ways of combining them to reconstruct exactly y. That's what we've been talking about in the first part and this part. The model is too flexible, and I have several solutions to reconstruct y exactly. So the numerical procedure is unstable, and also I will overfit my training data. So I want to reduce the number of columns in X, as we said, and to keep only k columns. If I were doing feature selection, I would just delete some of these columns, for example, keep only the first 3. But maybe I can find some other way of building a set of k, for example, 3 columns in the column space of X that reconstruct Y reasonably well, but with a limited number of parameters. And
yeah, so just a quick question. Or I guess the clarification that was useful to me. When you're doing feature selection, the columns values of X don't change for the ones you have keeping. The whole point of this matrix decomposition or transformation, the what you call as a family of k vectors or the set of k vectors will have a different representation of X. Is that fair to say?
Thank you. Yes, exactly. So if I was doing feature selection, I would look at Y, and then I would look at the columns of X one by one and decide, okay, for example, this one, it doesn't look at all like Y, I drop it, this one also, but maybe this one and this one and this one, they're a bit aligned with Y in some way. So I will keep these 3, for example, and find a way to combine them to reconstruct Y. That's feature selection. I don't modify these columns, I just select which to keep and which to remove. And in what we are doing now, I will construct new n-dimensional vectors, so new columns where I have one number per participant in my dataset that are a small number of such columns, but that I can combine in a way that they reconstruct something that is close to Y. And I do this by computing a factorization of X. So here is the same matrix X with all of its many columns. And I want to approximate this data matrix with a multiplication of 2 much smaller matrices. So for example, if I want to keep only a set of 3 vectors, so reduce the dimension to k, one thing I could do, as I said, could be to just keep the first 3 columns of X, for example. But what I will do now is to find the best possible pair of matrices, the first having 3 columns and the second one having 3 rows, such that when I multiply them, I get something that is very close to X. So I set k that is smaller than the rank of X, the dimension of X in either row or column direction. And I try to find these 2 small matrices such that their product is a good approximation of X. And here I have, since here there are few columns in W and few rows in H, in total here, I have a much smaller number of values than in the whole matrix X. But even so, this product of two small matrices, when I compute their product, I get a good approximation of X. So in a way, I have summarized my design matrix, my data matrix X, with a much smaller number of values. And here as well, I will say that I have a good approximation of X when I have a small sum of squared errors between my approximation and X. So for each cell in this matrix, I compute the square difference between its value in X and its value in my approximation. And I say that I have a good approximation when this sum of squared errors is small.
So it is similar to the mean square error concept that we learned before, but this is more applicable to the matrices. Would that be a good way of thinking about this?
Yeah, it's the same criterion. So this approximation here of the first column of X is close to X if their square distance is small. In the same way that here this approximation of Y is close to Y if their square distance is small.
Right.
And now that I have built this summary of the data matrix X, instead of trying to write Y as a combination of all the columns of X, I try to approximate Y with a combination of these few column vectors that I use to summarize X. So I constructed this small family of n-dimensional vectors W, and now I will regress Y on W instead of regressing it on the full X. So now I only have 3 parameters to estimate in this example, and it becomes easier to identify right away what are the good coefficients to reconstruct Y by mixing these three n-dimensional vectors.
Yeah, another little note, I guess, because they're kind of used interchangeably sometimes. When you say you're trying to regress Y onto W, it's kind of similar to saying, okay, you're going to use now W instead of X to predict Y, because that was kind of the language you were using before, but they essentially mean the same thing.
Yes, thank you. Yeah, that's exactly correct. So I just replace X by W, and now I have to find, so now the vector of parameters I'm looking for is 3-dimensional, and I just have to figure out how to mix together 3 columns instead of p columns in order to get a good approximation of. And then when I get, once I have fitted this small vector of parameters beta, which is now much easier because I'm a smaller dimension, when I need to make a prediction for a new point X, for example, in my test set, I just first find its coordinates here in the space spanned by W. So I regress it on my matrix H, and once I have expressed it in the 3-dimensional space, once I have represented it in this 3-dimensional space, I multiply it by the 3-dimensional coefficients that I learned in this step, and I obtain my prediction Y for this input vector. So that's the basic idea of these decomposition methods. First, we simplify the input by computing a low-rank factorization by writing it as a product of 2 small matrices. And then we use this small matrix instead of the full X as our design matrix to fit our linear regression. And now we'll talk about one of the ways that this can be done, which is called principal component analysis. So that's one method for doing this kind of linear decomposition. And the idea is to compute the singular value decomposition of X. So X, like any matrix, can be written as the product of three matrices. U, which has orthogonal columns that span the column space of X. S, which is a diagonal matrix with positive and decreasing numbers on its diagonal. And V transpose, which is also an orthogonal matrix, this time spanning the row space of X. So I'll show an illustration in a minute. But basically, we compute this factorization like this with the fact that this matrix multiplied by its transpose is the identity, and the same for this one. And here, the columns of V, the rows of V, sorry, the columns of V, the rows of V transpose are called the principal components. And they point in the directions where the first one points in the direction where X varies the most, and the second one in the second direction where it varies the most, and so on. And as I said, they are orthogonal. So for a two-dimensional example, here would be the first principal component in the direction where there is the most variation in X, and here would be the second one. So we can compute these two factors one by one. So again, we start from X and we try to build two matrices U and V such that their products gives a good approximation of X. And we start by the best set of only two vectors to build an approximation of X. So here, as you can see, the approximation is very bad because we're trying to summarize X with only the outer product of only two vectors. But then once I have selected the two that match the most closely X and explain the most variance, I look for this second pair that further reduces the error as much as possible, and that will be orthogonal to the first pair. So U1 and U2 will be uncorrelated, their inner product is 0, and the same thing is true for V1 and V2. And like this, one by one, I find all my principal components, each time by looking for the pair that reduces as much as possible the error of the previous approximation. And we see here that with only three vectors, so by computing the sum of just three pairs of vectors, the outer products of three pairs of vectors, I can already get a good approximation of my data matrix X.
Yes, so this is actually a really good illustration of reconstruction. I think it's really nice. Yes, a couple of things I wanted to ask is it unique, first of all, the decomposition? And so also the extended variance, what does it mean in terms of this reconstruction?
Yeah, so yes, it is unique. Yeah, it is unique unless some of the singular values have a multiplicity. So here I look for the direction where X varies the most, and then the second direction where it varies the most. If here it happened to be a perfect circle, which won't usually happen in practice, then I could then both the first singular vectors would correspond to the same singular value, and I could find it. I could use any pair of vectors that span this space, but in practice, in real data, yes, it will usually be unique. And the explained variance is basically 1 minus the variance of the error that remains once I have approximated my data matrix X. So
Right.
if the explained variance is 0, I have just fitted the mean. And if the explained variance is 1, it means that I have perfectly reconstructed my matrix X.
Right. And so this order is also important, right? So the S1 will be the biggest, the first component is the biggest explained variance,
Exactly.
and it will decrease in their order. Yeah.
Yeah, so here I'm just looking for the pair of vectors that give the best possible approximation of X. So I start, yeah, and then once I have found the first two, I look for the second pair of vectors that reduce the residual error the most. So at each step, I'm looking for the single best pair of vectors that I can find to reduce the reconstruction error as much as possible.
Cool. I guess just people who don't have background in linear algebra, I think it's okay if you don't understand the matrix equations. I think it's just important to understand the concept of reconstruction of your data. And I guess you could also use the explained variance to pick the number of components you want to keep when you're trying to reduce the dimensionality. But yeah, just want to say that it's okay if you don't understand all the equations at this point.
Yeah, I completely agree. The important thing to remember is that we have our matrix X and we try to summarize it as the product of two much smaller matrices. So we may pay a small price by using an approximation of X instead of the exact inputs, but we gain because we now have a much smaller matrix. So we have removed some noise and we have fewer parameters to estimate. So our model is likely to be more stable and should generalize better to test data. And then the singular value decomposition is just one way of finding these two matrices. But it's the one that for a given k will give the best possible approximation in terms of the squared error. And also we have the fact that these matrices are orthogonal, which means that here, when I have an input X and I need to compute its projection, that's very easy to do because it's just a matrix vector product. I don't need to compute an actual linear regression. But yeah, as we said, PCA, so principal component analysis or SVD, is just one way of finding such a summary factorization of X. And if I put different constraints or penalties on the two factors, W and H, for example, in some cases, depending on my data, it might not make sense to have negative weights in this linear mixture, so I can enforce that all the weights be positive, or I can put different kinds of constraints and penalties, and this will yield many different flavors of dimensionality reduction. But in all cases, I'm just finding a pair of factors that approximate well X, usually in terms of the sum of squared errors, with some constraints on the two factors. Now, one thing you might have noticed is that in order to compute this SVD or these factorizations here, I'm not using Y at all. And whereas when I was doing feature selection, I was looking at the associations between my features and Y. So there are ways that combine these two ideas. For example, the partial least squares, that will look for linear decomposition of X while looking for the directions that are the most associated with the output that I try to predict. But this version here, PCA, is an example of unsupervised learning, which means that we just try to look for a good representation of the input vectors of the design matrix. And at this point, we are ignoring Y. So we don't use Y at all. to fit the PCA. Just a small note, because we talked before about ridge regularization, so L2 penalties on the coefficients as a way to stabilize the model coefficients, and now we talked about PCA. They are actually quite similar, because in all cases, still linear regression, we try to write Y as a linear mixture of the columns of X, and in both cases, what these procedures do is compute the SVD of X, and then find the coordinates of Y in the space spanned by the first factor U. And then the only difference is that in PCA, we set the number of components that we keep K, and all the others we set to 0, while the ridge regression, instead of completely deleting these dimensions, it will simply shrink the coordinates of Y along these directions. So in a way, it's kind of a smooth version of truncated SVD of PCA, where instead of setting some coefficients exactly to 0, we just reduce their size. And of course, both can be combined. So it's possible to first fit a PCA, reduce the dimension of the inputs, and then fit a ridge regression. Okay, so that's it for our discussion of unsupervised learning or dimensionality reduction. And now we'll talk again about cross-validation and how we set these hyperparameters. Do you have any questions at this point?
No, I mean, I guess just to keep in mind that, okay, so even the PCA itself is unsupervised, we often use subsequently for a supervised problem. So just by itself, it will reduce the number of features that you're using, but then we will use those features to predict something. And that's where the whole cross-validation framework comes into handy.
Yeah, exactly. So when we do a PCA to reduce the dimension of the inputs to our regression, we need to decide how many principal components to keep. Or if we are fitting, for example, ridge regularization, as we saw in the first lectures, we need to decide which lambda, which hyperparameter to use. And the way to do this is to fit several models with different values of K's and lambda, and then keep the ones that keep the one that produces the best prediction on left out data. So why we need fresh data, just a small illustration of why we need a separate test set. Imagine that I have, for example, 4 dice, and I want to find the one, I think that some of them might be loaded. I want to find the one that gives me on average the highest possible number. If I roll all of them once, and then I keep the one that gave me the highest number, usually it will give me a number that is quite high, that is bigger than its expected value of 3.5. But if even if the die is not loaded, just because among the several options that I have picked the best. So for example, here I have many dice. Each gray line corresponds to a die. I throw them all, and here I pick the best, and I look at the value of the highest die that I found. And every time it's quite high. But then in the next roll, if I look at the same die again, I see that it will oscillate around 3.5, so around its true expected value. So if I look at the value, at the experiment that I used to select the die in order to estimate its expectation, I have a biased estimate, because by selecting the best, I have made it more likely to end up with a high value. So I need to select the die by rolling it once, but then not keep this value that I found and roll it again in order to estimate its expected output. And that's exactly what we do when we separate the test data. We roll the dice once for all the models, select the best model, but then we discard the score that it got in this first roll, and we evaluate the model again on a new data set in order to estimate its actual performance. So basically, whenever we select the best among several options, or when we find the maximum of something, we don't use the same value that we use to select it in order to estimate its performance. Once we have selected it, we discard the value, the criterion that was used to select it, and we evaluate it again on a fresh batch of data. So for example, when we set the parameters, when we fit the model, we select the parameters beta that give the best prediction on the training data. So here we have made a selection, we have picked the best. That means that in order to evaluate it, we don't keep the score, prediction score on the training data. We discard that, and we bring in a new fresh batch of data and evaluate the estimated parameters on this new data. And then for the hyperparameter, for example, lambda or the PCA dimension k, it's the exact same thing. Once we have fitted beta for several models, once we have several models on the validation data, we evaluate all of them and we select the best model. So again, there is a selection. We have kept the best models among all that have been trained on the training data and validated on the validation data. So because we have selected the best, again, we discard the scores that were used to determine which is the best, and we bring in a new batch of data, the test data, and evaluate again a single model, which is the one we decided to keep. So that yields to that results in the 3 splits that Nikhil described in the first lecture, where on the training data, we find the best beta for each hyperparameter or for each model. And because we have chosen it here, we evaluate it on a different data set, which is the validation data. On the validation data, we evaluate the fitted beta and we choose the best hyperparameter. And here we see that we have chosen something. So again, we need a new data set in order to evaluate it. And finally, on the test set, we evaluate the model that we have selected and its parameters.
Sorry, just a couple of notes. If you go, So in the dice example, you're basically saying that the analogy is between each die being a model. Is that correct?
Yes.
So so if you do run a bunch of models, some of them are likely to give. They can always give much better performance than they're expected to be, and that's why you need to evaluate them again. In the second, if you go down a bit, So for this, so for this thing, if you think of in terms of say PCA regression, what would be the lambdas and betas here?
So betas would be the parameters of the linear model that I learned that determine the linear function that maps the inputs x to y. And lambdas would be the hyperparameters, so the possible values either for the regularization hyperparameter of rich regression, or for the number of principal components that I keep, or for the number of features that I keep when I do feature selection.
Great.
So with this hyperparameter, for example, number of features, I have a set of different possible models. For each of these possible models, I adjust their parameters beta by fitting the training set. So if I have 10 possible values for the number of features, for example, I end up with 10 fitted models. I evaluate each of them on the validation data. I end up with 10 scores. And I keep the model that produces the best score. Then this score that I use to select this model, I discard it. I keep the model, evaluate it again on a fresh batch of data, which is the test data. And then I have finally an estimation of how well my model will perform on new data. And as you explained in the first lecture, when we do this, we end up using only a small part of our data to fit the model. So to use more of it and also to fit several different models and get a better estimate of their prediction performance, we do cross-validation, where we we do several splits of the available data, and each time training on one part, validating to select the hyperparameters on a different part. Once I have selected the best model like this, I'm not forced to, but I can refit the model with the best hyperparameters to the whole training and validation data. And then finally, I evaluate it on some test data that hasn't been used at all in the first part. And then I can repeat the same thing for a different split. This is what does the grid search CV in scikit-learn, that implements this whole procedure for you for selecting the best hyperparameters, that implements basically this part of the procedure. The CV to select hyperparameter and refit. Yeah.
Yeah, just a small, I guess, note/question is like, okay, how do we pick how many train and test sets do we have, or validation sets here?
Yeah, that's a good question. We don't want to reduce too much the size of the training data. So if we say we do k-fold cross-validation, which is a very standard choice, which is what is illustrated here, we divide the dataset into several parts, and each chunk of data will become the test set at some point. So here it's threefold cross-validation because I have divided the data into 3 chunks. If I set k to be very small, as I did here, I'm only using here 2/3 of the data to fit my model. And I also get very few validation scores. I only get 3. So by using little data, I get a model that is maybe worse than what I would get if I fitted on the whole data, and I have less cross-validation scores. On the other hand, if I set k to be very large, so if I used 50 instead of 3 here, I would use almost all the data to train my model, but I would evaluate it on very few points. So my my average score would be very noisy. And also, I would be using almost the whole data to fit the model every time. So I would be more or less using the same data in each cross-validation fold to fit the model. So I would be training the same model in every cross-validation fold. So I wouldn't get a good account of the variance that is due to training the same model on different datasets. So I try to find a trade-off between these two things, either so that we don't have too few folds nor too many. And typical values that people use are between 5 and 10 cross-validation folds.
Yeah, also, I guess a small note here, if you might be confused, if you see large computer vision data sets, especially in machine learning or deep learning, they have hundreds of thousands, if not millions of images. So they usually don't do the cross-validation. They just pick one large train, one large validation, one large test set. Because if your data is large enough, we don't have to worry about these issues that much usually. But therefore, that you need large amount of data.
Yeah, there are 2 aspects to cross-validation. One is to be able to make an efficient use of the available data. And the other thing is that here we are training different models on quite different training data sets. So like this, we sample a bit, although they overlap, so they are not really independent, but we sample a bit the variance that can be introduced by training the model on slightly different data sets. And that's not something that you can evaluate if you fit only one model and test it only if you fit and test only one model. So even with a large data set, it might be interesting to fit and test several different models on different subsamples of the data. Of course, if you have a huge data set, you could always divide it in completely distinct chunks and then divide each chunk into fit and test data. If you think it's okay to fit it on a much smaller training data set. Just to conclude, I'll list some possible mistakes with cross-validation. So the first one is to fit part of the pipeline on the whole data set instead of only the training data. For example, we talked about PCA. Imagine that I start by saying, okay, I will do my unsupervised learning. I will fit a PCA to reduce the dimensionality of X. And then I will use the reduced dimension design matrix to fit my linear regression. What I could do is fit the PCA on my whole X, whole design matrix X, obtain a dimensionality, a smaller version of X, and then do cross-validation on this smaller version of X and Y. But that would be a mistake because the dimensions that I choose to represent X have been informed by the whole data set, including the training data points. So we have to be very careful to set aside the testing data at the very beginning of the whole procedure and not use it for anything at all, neither fitting an actual regression model, but also we cannot use the test data to fit linear decomposition or to do feature selection or anything at all. It seems obvious when we say it like this, but sometimes it's hidden in the middle of many lines of code, and this kind of mistake can sneak in. And there's something called the pipeline in scikit-learn that makes it easy to make sure we fit everything only on the training data. Another mistake is to make an error on what is a statistical unit in our analysis, or to ignore the dependencies between the training samples, the rows of X. So for example, imagine that I'm trying to predict fluid intelligence, and I have several brain scans for each participant, and I fit my model to predict fluid intelligence based on the brain scan. If I want to generalize to new participants, then I must make sure that I don't spread the data from one participant across training and testing set, because I want to be able to make a prediction on new participants that I have never seen before. So if I evaluate my model on participants on new data, but from participants whose first scan I have already seen, I'm performing a much easier task. Another example is time series. If I shuffle all my data and then do the prediction, I'm just interpolating between points in the time series, which is much easier than making a prediction on a time chunk in the future, for example. I'll show an illustration of this in a minute. And then one mistake that is quite common is to ignore the fact that the training data sets overlap. So the scores I get for each cross-validation fold are not independent, which means that I cannot really estimate their variance. And therefore, it is a mistake to try to do some hypothesis testing, some statistical inference on the cross-validations, on the scores I get from my cross-validation procedure. So when you see, for example, someone doing cross-validation for two different models, getting 10 scores if they do 10-fold cross-validations, and then doing some statistical tests to compare the two group of test scores and concluding okay, with such significance, model A is better than model B. That is a mistake because the data doesn't respect the crucial hypothesis of this test that the samples must be independent. And finally, it's easy to overinterpret good cross-validation scores because by construction, since I have sampled the data uniformly from one single data set, the testing and training data, they come from the same distribution. But if now I bring, for example, participants from a different hospital, they may differ from my training participants in ways that just sampling, training, and testing participants from one data set do not reflect. So if I take one data set coming from one hospital, I split it in training and testing, okay, the data doesn't overlap, so I see some kind of generalization. But even if I get a good score on this test data, if now I bring an image from a different hospital acquired with a different scanner, the model may not generalize as well to this new data that comes from a different distribution. So just an illustration of what I said about time series. Here, I have a time series as my input, and I try to predict y. So here I have my input x, and in this direction I have the output y that I try to predict. And in orange I show the test set, and in blue the training set. So for example, here I train on all years up to 2015, and I try to predict what will happen from 2015 to 2020. And in the second example, it's the same thing, except that I have shuffled all the time points between before splitting between training and testing set. And we can imagine that predicting this data from this one will be much easier than here interpolating between nearby points to predict the values for the orange triangles in this case. So even here, I have perfectly separated training and testing data. They don't overlap, so I'm doing cross-validation with the held-out test set. But because of the dependencies between these data points that I have ignored, I'm performing a much easier task than what would be true generalization to some unseen data that might come from the future. And again, yeah, I remember when we fit these models with cross-validation, the train sets overlap, so cross-validation scores are not independent. Now we are running out of time, so I was going to just briefly describe the prediction pipeline that we will implement in the tutorial. It will be predicting which site an image comes from based on functional MRI data. Nikhil, do you have something to say to conclude this session?
Yeah, so just a couple of little notes. Yeah, the cross-validation can get tricky with temporal dependencies or even group-wise dependencies, but scikit-learn does have pre-built functions to take care of this. So you don't have to manually keep track of this usually. You can definitely do a group-wise separation for your stratification of your validation sets using pre-built functions in scikit-learn.
Yeah,
you just have to be aware.
Yeah.
You just have to be aware that these type of things can go wrong. Otherwise, you will just not know about them. No, that's pretty much it. I think we will discuss more in detail about the prediction pipeline that we'll be building, and we'll be comparing some of the open source neuroimaging data sets to build a classifier. And we'll go over the classification as well as the future dimensionality reduction tasks in the pipeline. Yep, that's all I have. Thanks so much.
Thank you.
We'll see you guys in the
Thanks to all for listening, and see you in class. I'll stop recording now.